So thanks to Vectric for hosting me. I'm on the Vectric Maker Hub workshop area that's in the middle over there. So I'll be there the rest of the afternoon. If you haven't already seen this up close, then it's over there. And welcome to Maker Central. So on relatable content and building it for clicks, who here hasn't seen a bicycle? Has anyone not ridden a bicycle? So everyone knows what a bicycle is. So I guess from a piece of sort of machinery everybody knows, everybody can relate to a bicycle and what bikes are supposed to look like. So on building it for clicks, for people to click on, I say let's make bikes weird. So this is the first omnidirectional kind of bicycle idea that I had, which if you take a close look at it, has a wheel on the wrong way, with lots of wheels round it. And so that wheel is parallel with the handlebars, essentially. So this wheel was made out of wood and I think the metal is cold rolled wrought iron that I got from B&Q or somewhere. I did have little T-pieces welded on the end of the spokes, so they fitted in those slots. And then I welded some axles all around and fitted skateboard wheels, which are 72mm longboard wheels, to make an Omni wheel. So this was the simplest way I could think of doing it. You'll notice the wheels are all square, so there's lots of gaps and there's lots of flats. And it weighs a lot because of all the cold rolled wrought iron and then 2 bits of plywood sandwiched together. This project's got a bit of Colin Furze in, so I don't know if you've watched many makers on YouTube. At Christmas we do this Maker's Secret Santa, where we all make something for the next maker, and there's typically 12 makers. And we all make something and it goes around in a big loop and we pass it around, and somehow we get all the videos out on the same day and everyone's gifts are received and everyone's sent and they all go out and it's a big chain and it goes around the loop, and it's really good because you can follow the loop all around and find the other makers who you haven't seen before. So Colin Furze made me a funny bike with a different funny wheel on, which was the Wheel of Feet, and he based that on a project I did, which is a small crawler that had these wheels, and there's basically a track on the inside and the feet slot in and out as they go round, so it's flat on the bottom and the former can kind of tilt and it can climb up things. So this is based on an old patent which never stuck around because it doesn't work very well. So basically no original ideas in any of these projects, all just recycled stuff from the past. And so I needed a bike for this project, so I did ask Colin if I could cut the bike up that he'd sent. Just wanted to check it wasn't his a sentimental attachment from his childhood or something like that. But he was fine with it, and he said, he guessed, is it a balancing bike? And obviously this bike's a bit weird, so it's not going to work unless it helps you a bit, if you can imagine riding it otherwise with the wheel spinning the wrong way. Great, so I cut the front forks off and welded on some extensions, and then taking a leaf out of Colin's book, let's make it all out of steel. So I welded on some box section and then a 20mm diameter piece of bright steel bar sticking forwards so that I can get the wheel on the wrong way round. And there it is. The wheel is powered by a motor this way, and that's a brushless motor. There's a 2-stage belt reduction, some big slabs of aluminium clamping it onto the forks. And then there's an O-drive, which is an open source brushless motor driver. And there's an encoder on the back of the motor, there's an encoder. And so the O-drive can accurately velocity control or hold the motor still and hold the wheel still. So there's the whole bike in all its glory. So we've got, you'll notice an emergency stop on the handlebars. I've continued with that theme through all of these. So the emergency stop, and we've got a switch that turns on balancing side to side. And then we've got a controller on the crossbar, and that's got some electronics in it. So, and there's a battery, a big LiPo under the seat. So here it is in action. This is the wheel held still by the holding power from the motor driver and the encoder. So you can ride it like a normal bike because the little wheels on the Omni wheel roll along. There's a close-up coming up. So the wheel still, apart from having tiny wheels to run on the front, it handles just like a normal bike. But the idea is that you can ride up, turn on the balancing, swivel round 180 degrees and ride off in the other direction. So there's going from balancing to not balancing, turning off the balancing. And now this is trying to do it the other way. And this is quite important. So what you'll notice is it's really hard to just turn it on. One of these times I forgot to turn it on, but the other times it did turn on. And you'll notice there's this sort of kick it does as I turn it on. And that's for a reason that I'm going to talk about. I'm going to talk about how balancing robots work a bit later, and this is quite an important thing. So I did eventually manage to do it, but it's still a bit sketchy. And this is probably the best footage of spinning around and then riding off. So normally I have the balancing off when I'm riding, but if you've tried to turn it on, then a weird thing happens. So on a bicycle, if you're trying to turn left, if you're not already leaning that way, you tend to do a little hook to the right and then turn left. But what happens on this bike is the active control takes over and keeps you going, and you're desperately trying to fight it, and it's still going off. So the specification of this, we've got one Omni wheel with 16 horrible square wheels with gaps in between, the O-drive and a brushless motor. It's running 24 volts at 20 amps, which is 480 watts, which seems like quite a bit. And the microcontroller in there is a Teensy 4.1, which is one of the fastest microcontrollers. It's Arduino compatible. It's something like, it's an ARM Cortex M7. A complete overkill. You can build a balancing robot with an Arduino 8-bit Arduino Uno, but it's nice and thin and it fits in the box to fit on the crossbar. And the inertial measurement unit that measures the angle is an MPU 6050. That's an Adafruit branded one, but you can get them for about £3, and they're okay. And pedals to power it. Good. Despite this shaky engineering, the video has gotten 3 million views. So there was a couple of years ago I did that. So from my point of view, that's more than 10 times the average views. So I succeeded in making bikes weird and people clicking on it and watching it, and YouTube liked it and showed it to more people because they thought it was popular. I don't really like the way it says gotten 3,133,000 views. It seems it's American vernacular, I assume. I googled Gotten to see if it's a word, and it turns out to be a place in Somerset next to West Monkton. So what's better than one Omni wheel? We're not here yet. It's 2 Omni wheels. So this looks a bit better, doesn't it? Maybe it'll be really good. So despite being perfectly capable of making a balancing robot, I've built quite a few other balancing robots that work perfectly well. There's enough brushless motors out there and everything you need, really, Arduino libraries. I decided what we'd actually do was take the guts out of a hoverboard, which is the first bad decision. So a hoverboard, if you haven't ridden one, balances like a Segway, but it's split in 2 halves. So essentially what you get for not very much money, relatively, is 2 balancing robots. And it's got foot switches, so when you stand on it, it firms up and starts balancing. But essentially, you turn by turning your feet like this. And if you move them back, you go one way, and if you move them forward, it goes the other way. And it feels there's quite a lot of torque in a hoverboard, it feels like. And all the electronics and everything's in there, and motors. So I thought, we're making this bike with 2 Omni wheels. We'll just take all the guts out. I don't have to do any hard work. So this is the inside of the hoverboard. So there's one of these boards on the left in each end, which has got the inertial measurement unit in that measures the angle, the motor driver, everything. They've got some wires linking them, the motor on the end. So I just took the motor, and I thought I was being clever here. So the wheels are much bigger than a hoverboard wheel. So if I just put that wheel on the hoverboard wheel, then it'd be much bigger. So you wouldn't have enough torque, really, to drive it. And also go much faster because of the bigger circumference. So I decided I'd velocity match the original wheel with the big wheel, which is why there's a belt drive that's going down. I put a 3D printed pulley on the hoverboard wheel to get the same velocity, because then I thought the hoverboard electronics will be really happy. It will go the right velocity and it will balance properly. The hoverboard's in 2 halves, so I split the bike in 2 halves. So there's these little windows, and each one of them has got the hoverboard electronics in there. The bike has an axle that runs all the way through, and then it's got foot pegs, so you can sort of move the back half one way and the front half the other way to try and turn. And the orange tape on the electronics is the sensors where the foot switches would have been, so it thinks there's always someone standing on it. I then scrapped that idea and decided to do this, which was an active control joystick, which when you move it one way, it uses servos on these seesaws to move the hoverboard electronics, like your feet are moving them, And then when you move it sideways, it moves them both sideways. And I'm not really sure why I needed to do that, because you can just lean sideways. So this was the third bad engineering decision. I forget how many were on. There's more. Because it meant there was nothing to hang on to, because it's horrible and soft. It seemed like a good idea at the time, though. So these are the Omni wheels, which are actually pretty good, although they weigh about 10 kilograms each, which is important. So this time, you'll notice they're a contour. Instead of being flat wheels, they're rounded, tapered wheels. And also, to fill in the gaps, there's two sets of wheels, and one set overlaps the other one, so they're actually round. So this is an IKEA table that's 1 meter 20 by 60, or whatever those cheap IKEA tables are. So they're quite big wheels, and they're mostly 3D printed. There's 2 plywood discs in them, and then the orange things I'm calling noggins that hold the wheels are all 3D printed with a 1.2 millimeter nozzle. And then the wheels themselves are 3D printed TPU tyres with a rigid core and a bearing in each end and a steel axle. So it's at this point I need to say thanks to my 3D printing sponsors, which is Lolsbot 3D printers, I've got 10, and 3D Fuel, who send me literally pallets of filament. So anything I make that's 3D printed's free. So the first bike had pedals to push it, and this one hasn't, and it's got 2 Omni wheels. And the little wheels are just passive that spin round. So I decided what we're going to do to propel it forwards was blow it along. Is this four bad engineering decisions? There's still one more. So what we're looking at here are these little ducted fans, which are quite high power, actually. They're 80 amps each at 24 volts, which is 2 kilowatts. So there's 8 kilowatts of fans to blow it along. And I was pretty sure this was going to work, because I've already used these exact same 4 EDFs, electric ducted fans, to blow me along. I did a project last year entitled "Why Single Caster Skates Are Easy." And so literally I was on single casters blowing myself along. And it was terrifying, but it did propel me, so I thought, that's going to be fine. Great. So a specification, we've got 2 Omni wheels this time, which are custom made, so they're nice and round. The hoverboard electronics, and it turns out the hoverboard is only rated at 350 watts, which is less than the first bike. One of those one wheels, that's the wheel that's like a board I decide you stand on, they're about 750 watts, but we're still quite underpowered here. The bike turned out to be a 2-person lift without the wheels on. So 350 watts for balancing and 8 kilowatts of fans. So this is my initial can I blow myself along test. The fans are really powerful, actually. They're really quite good things. But you can see my plant pot. Like, that's quite a lot of air. So then the next, I forget what we're on now. I decided that because of building it for clicks, I'll add some more mass to it and dress it up as a Star Wars speeder bike. So, was anyone here yesterday, saw Matt Denton's talk? He's worked in the movie industry, he's around, he's on the bill. So he's a good friend of mine, he lives in the same town. So Matt Denton had to help me push to get it going. It blew his t-shirt off, because he was right behind it. But I got one good run out of it. It was a bit, you can see there's nothing to hold on to, it's going all around. The rest of it wasn't so good. Yeah, it's got very sketchy. So basically those wheels, there's so much torque needed because there's so much mass, plus everything else attached to it, and the fans blowing. So altogether, probably, it was just like, if I thought about this before I started, just like Star Wars though, there we go, I probably wouldn't have done this. Success, 3 million views since last October. And that's part 2. I did a part 1 that had 500,000 views. There we go, it's probably the Star Wars that did it. What's better than 2 Omni wheels and blowing myself along? It's 4 wheels, but these are slightly different. So you'll notice that these have the little wheels all around them are slanted at 45 degrees. So these are called mechanism wheels. As soon as I made the last wheels, I thought, oh, I should have made mechanism wheels, but I'd already made these huge wheels, and there's always time for another version anyway, so Normally, mechanism wheels would live on the corners of a robot. So this is another thing I built a while ago. You get forklift trucks with them. So basically, they screw against each other, and it means it can go sideways. So if you've seen Colin Furze's screw tank, 2 big screws drive it along. If you've got those screws and put them end to end and made them shorter and had 4, it's exactly like that. Only the little wheels on these are passive. They spin round, so instead of churning the carpet up and cutting holes in the ground with a metal screw, slides nicely. So I kind of thought I'd invented this idea of putting them in a row. I mentioned it at the end of the speeder bike video, and someone sent me a link to a PhD project from 5 years ago, Sheffield University. Someone made a little one, though. So I'm still calling it the world's first screw bike, because no one's made one you can ride on. And it was at that point I knew it was going to work as well. So I made the wheels again. So these, again, are mostly 3D printed. There's a wooden disc at each end. And the hub is 3D printed with a 1.2mm nozzle on Lolspot printers with 3D Fuel Pro PLA+. Everyone's got a metal axle again. Oh, thanks to Simply Bearings for the bearings for all these. Those are free as well. And since Vectric, this is a Vectric stage, the pulleys and all the plywood's toolpathed with Vectric Aspire. So there's wood in it, which is good because you can buy it in wicks. So, and it's quite cheap and rigid and light, relatively. So I've got 3D printed CNC wooden pulleys, which is fine. The teeth are quite small, but because they're so big, the belt's got lots of traction around for all of those teeth engaging, rather than having little gears with 1 or 2 gears engaging. So I made 4 of those. Yes, it was a lot of work. And I remembered to make mirrored pairs, because if they were all the same and you tried to screw along, that's the same as rolling sideways. So they have to turn in opposite directions so that it stays in the middle and goes, hopefully, linearly. The frame is steel. So all of these parts didn't seem that heavy, really. Oh, it's not much heavier than a normal bike frame. All these wheels are plastic, they're light. Anyway, it's about 60 kilograms in the end. So that's the frame, and the important part is the 4 risers that you can see there. You can probably see how this relates. We've got these foot pegs, and then we've got the top is where the saddle is, and then we've got these risers, and those are basically where the motors go. So thanks to O-Drive for the motors, this is the new O-Drive servo kit, which is a 1 unit essentially. So the motor has a magnet on the back, and the board has a magnetic encoder. There it is. And that sandwiches on the back. And they send you all the mounting plates. And then you basically make this servo kit. So all you have to do is send power to it and data, either serial or CAN bus. There's an Arduino library for it as well. And that makes this motor unit, which can be velocity, position, or torque controlled. So there is an intermediate pulley. It's a different one to that one. And that's because this is footage from the project I took the motors off. So if you've watched any of my previous videos, you'll remember this thing I did with Colin. There he is. So another bit of furs in it, where I got stuck in the same river he did with the big version that he's got over there. So there's actually, if you look closely at this, these are the actual same prints. There's still river mud all over them. So that's the motors are essentially, they're limited to 1.5 kilowatts each. You can push more into them. So those fit on those risers on the chassis there. And they're tensioned with blocks underneath, so I can pull the belts up. And yeah, here it is with the controller on. I've got the headlight does work for those of you who, I'll turn it on later, there we go. Nice bulk headlight, and this retro seat, which is apparently off some Honda thing, but I just went on Amazon and looked for a bike seat. So just finished off the style nicely there, really. So what's really important, though, is making it balance. Balancing is one of the most important things in these projects, which is where the other 2 kind of went wrong, really. So in order to make a balancing robot, we have something that measures the angle. So we have an inertial measurement unit, and that's what you've got in your phone that allows you to use it as a spirit level, or you can play a game driving. It's quite accurate, or turns the picture the right way around, turns the screen rotation round. The inertial measurement unit has a gyro in it, solid-state gyroscope, which measures rate of change. So as you turn it, it will give you a spike of data, and when it's still, it gives you nothing, or zeros. The accelerometer will measure the actual angle, an absolute angle, and as well as linear acceleration, but it's very slow. And then the magnetometer is like a compass. So in the past, you'd get all this raw data and you'd have to filter it together and try and get the angle out of it. This device is actually pretty good. It's designed for VR headsets, and it's made by Bosch. And Bosch programmers are better than I am, so they do all that on the chip. And then SparkFun Electronics, who make these red boards, which all come with Arduino libraries. Basically, they've got a library that just gives you the angle. So all you have to do is wire it up, use a library, and then you get the angle. So this is pitch, roll, and yaw. The graph at the top is pitch and roll, and the bottom is the yaw. And it does that whichever way around you put it. So it essentially is 9 axes, 3 gyros, 3 accelerometers, and 3 magnetometers in each of the 3 axes. It's a very useful thing. So what we need then is a controller to drive the right velocity of the wheels to make it balance. And so typically use a PID controller. So this is a diagram I got from Wikipedia. It looks like maths in boxes, but it's actually not that complicated. So there's 3 terms that you have to tune. The first one is proportional. And that literally means if the angle is bigger, the wheels go faster. And if the angle is 0, the wheels go 0. And if it's the other way, then you go the other way. So that's fundamental to balancing, really. And that seems like that would make it balance, but that's not enough. What you'll find is you can tune it so much, but it'll just keep going, and eventually it will fall over. So what we need next is the integral term. So an integration is quite easy, actually. It's the area under the graph. So if time is going this way, and the angle is some value, if the angle's 0, the output's 0, so the wheels are still. But if the angle is some value, and time is going on, then the area gets bigger. And so the output gets bigger. And so that means that the wheels accelerate towards the target to try and bring it upright and catch it. So also, if the angle's getting bigger and bigger and bigger, that area is getting bigger and bigger and bigger, and so the output gets even bigger. It's an exponential. So if I'm leaning on it really hard, pushing the angle more, it accelerates more to catch me. So that's fundamental to balancing robots. The last term is the derivative. So with all of that integration and that exponential velocity, it's very easy to get oscillations and get overshoot. So it'll go so fast and then overshoot where it needs to be, and you'll end up oscillating. So we use the derivative, another diagram off Wikipedia, which is the tangent, makes a sort of sharp motion. It's like the attack and decay of the acceleration to stop overshoot. But you don't have to worry about that because there's a library, the Arduino PID library, which you can just tune your parameters. You'll find most of it's integral, a bit of proportional, and a very small amount of derivative. And then you set the input, the set point, and the output. The set point is the angle you want to balance at, essentially, which in my case is 0, because I want to stay upright. If I wanted to make it radio controlled, I'd tie that value to a control stick, so I could set 2 degrees, and then it would have to keep driving to catch itself, so I could make the whole thing fly by wire. The input is the angle from the library for the inertial measurement unit, and the output goes to the velocity of the wheels. And again, there's a library for the O drive to communicate over CAN bus or serial to drive the velocity. And the O drive takes care of regulating that velocity. So it's actually pretty easy now to make a balancing robot. And understanding what the integral term does is the most important thing. I was there for some months in the early days trying to make a balancing robot, not really understanding it, randomly tuning values and hardly ever making it work. As well as that, we want to drive it along this time instead of blowing it along or pedaling. So we need to screw those wheels against each other. So all I did was, we've got a twist grip, and we add that value onto the balancing value, but rotating the wheels in opposite directions. And then to make it turn, the front wheels go one way, and the back wheels go the other way, and the inside ones go slightly slower because there's less circumference. And that's just added on as well from another twist grip. So I mentioned the first bike when I turned on balancing with a switch, and then there was a kick. And that's because of the integral. So if the bike is on, the electronics are on, and the PID controller's running, but the motors are not running, unless you can balance it perfectly at 0.00 degrees, that integral starts to increase. And it accumulates a massive value. And then when you turn the motors on, the motors are moving at a massive value, which is why it does this. So that wasn't so bad on the bike. This one's 50, 60 kilograms, so I don't want to snap my ankles off. So I've got some knobs. One of those is a volume control, so you can slowly turn it up when you turn it on until it's balancing, and then it's nice. The other knob is the trim for the exact 0 point. And yeah, a big emergency stop and some twist grips I'll talk about in a minute. So what the specification is 4 mechanism wheels this time, which are of course custom made. The Teensy 4.1 microcontroller, that's actually got CAN bus built in to talk to the O drive, so that's really good as well. The Bosch IMU, and then we've got the motor drivers and everything, and we're running 50 volts on this one at 30, is limited to 30 amps. I could push 40 into each one, which is, where are we, 6 kilowatts in total for balancing and for driving. And no pedals or fans. Good. So the whole thing's open source as well. So I'm never going to make this into a product before anyone asks me, and plenty of people have. So I publish all my projects as open source on GitHub. And so that's the code and also the CAD. So all of the design files, it's the closest thing you can get to source, which is step files, rather than just STLs. So if you've ever downloaded an STL and you want to modify it, that's really hard because there's a horrible mesh. Whereas step files are solid models, so you can load it into any CAD, resize the holes, scale it up and down, pull the faces in and out, stick bits on, cut bits off. So if you want mechanism wheels for your own projects, then you can download that and extract them and do what you want with them. Success! Here we go from a YouTube point of view. Did 1 million views. What's that? 1,185,000 views in exactly 7 days. So yeah, I was pretty happy with that. I think it's the fastest uptake of views I've had recently. And it's done 1.8 or something now, and it only went out a few weeks ago. So I've got a video of it working. So I'm just going to leave going while I mess about with the real thing. So they said, could I bring this on the stage to do while I do the talk? So I just took that to mean there's going to be a demo. So safety first. It's good luck if you break mirrors, right? I want to stick a stick on it with the light shining down, so the human mirror ball. But EMF camps in a couple of weeks, so you never know. So the seat's not fixed on, that's deliberate, so if it goes bonkers, I can grab the frame. So that's the extra safety feature as well as the emergency stop. Right, let's, so we've got an initialization switch that turns all the motors on. They should all be flashing green now. So now if I, oops, ease up that integral, there we go. Right, good. Let's get this wire out of the way. So that's just balancing now. You'll notice it wobbles a little bit, and that's because it's tuned. The PID parameters are tuned for me to be on it, rather than no one to be on it. That's why the hoverboard has those foot pressure sensors to change the parameters when you get on it. So I'm just going to turn this round. There's that headlight, for anyone who missed it earlier. Right, I should get on now. Good. Let's just sort out this trim control. Yeah, so obviously it goes sideways, right, like a Segway. So I've got, to control it, I've got twist grips. So to go forwards and backwards, there's one on my right, like a motorcycle throttle that screws it along. And there's also a direction switch, so I can go backwards. And then on the other side, I've got the same thing again for the direction. So the first Segways had a twist grip that moved in both directions on it for turning. I could have made one of those, but I didn't have time, so I've just got one that moves forwards. If the switch is forward, it turns right. And if it's left, if it's backwards, it goes left, which isn't a good steering mechanism. But yeah, so let's just see if I can get a good run out of it down here. Oops. I'll try not to trash the stage. Daisy Tempest's on next. I warned her that if it's all, sorry if it's all torn to shreds. Well, oh, fuck. Now we're good. I'm being cautious. That's right. Let's. I just really don't want to drive off the stage if I can avoid it. Right, here we go. Oh, that's the closest thing to going forwards. Great. So in the video, people complained there wasn't enough footage of it going forwards. But bikes don't go sideways, so I thought it was fine that there was more footage of it going around. So all of these mixed together, there's not much space on here. So I can actually turn and drive at the same time. We're going to go off the stage there. Let's go this way. Good. There we go. You'll notice in the video, if I drive in a circle, I have to fight it. So the centrifugal force pushes you out, and so it tries to drift. So you end up pulling it in that way. Yeah, that's basically the end. So are we doing questions? I'm gonna have to take this off so I can hear. I'll just stay on it and casually drift around.
I was scared of getting too close, man. All right, we'll start down here.
I don't blame you.
Hi there.
Hi.
So sometimes people like Furs will do videos with basic tools.
Yes.
What to you is the first non-basic tool that you would go for? The one thing you can sort of like, say you got 3D printers, drills.
Yeah. Oh, okay.
After that, what is the thing you would not want to live without?
Oh, so probably welding after that. So I tend to stay, if I can 3D print it, then great. And then if I can't 3D print it, then I'll CNC it, like the pulleys are too big for the print bed. And then if it can't be aluminium extrusion bolted together with 3D printed brackets, then it's steel.
And so extension from that, how much better do you find TIG welding over an arc or a MIG?
I've only really done TIG.
Right. Because it always looks so neat when you do it.
I don't want to make too many sparks, otherwise I'd MIG it. Stick welding I have tried, and it's very hard.
Thanks. Hey, James. So what we've heard here is that you're a couple of steps away from being able to make a self-driving bike.
Yeah, so this could be completely autonomous.
And you could call it to your location, couldn't you? Because you don't technically need to be on it to ride it. So I guess my question is, when are you going to do that, man?
Well, so what I found is AI projects don't do well in my channel. So I did do quite a lot of autonomous stuff with ROS, which took about a year to learn to do the navigation stack and everything. So yeah, this could be completely fly-by-wire. Like the sideways is just that set point. So you could have a omnidirectional robot with a LiDAR on it, or one of those Intel RealSense positioning cameras. I've played with all this stuff. But yeah, views are not 1.8 million for those bits of content. So maybe if this had come out as autonomous to start with, but I think actually putting yourself in the projects is probably, you know, look at Colin's projects, everyone's a funny vehicle or a pizza bike. So.
Do you have any other questions? Okay.
Hi.
Hi.
Have you ever tried to 3D print a belt?
Yes.
Or something.
In the when I first started doing, well, I first had a 3D printer in the days of ABS printing, because the toolhead didn't have a part cooling fan and everyone used ABS. But yeah, so I did this R6 droid as a Star Wars droid, and I did actually I printed V belts for that out of NinjaFlex. I never tried to do teeth, but you know, belts are quite cheap anyway. So these are HTD belts, which I think stands for high torque drive or something. They've got fiberglass, you know, bands embedded in them, and they're quite torquey and nice and thick. So they're really good for conveying force. Whereas your NinjaFlex be quite hard to get steel wires or something in. So yeah, it's kind of those things are just not worth it, to be honest. But you could do.
All right, let's get down here.
Do you find Arduino knockoffs like Elegoo, do they work as well as an Arduino?
I think those aren't the worst ones. But yeah, you can get, so when you buy 3 Arduino Unos for $9 on AliExpress, that's where it goes bad. But they're normally okay. It's normally just the voltage regulators. So if you run them on much more than 6 volts on the V-in, then they tend to fail, and all your NeoPixels start going weird, and weird stuff happens. But most of them are okay, actually.
All right, we're over here.
I've got 2 questions.
Okay.
One, which has been your favourite project to work on and that you're most proud of? And second, do you ever think you'll be doing more robotic stuff, or do you think you'll continue with the bikes and more of the omnidirectional?
Okay, so so I always say my favourite project is the one I haven't started. So it depends. So when I'm building something, it's not my favourite project at all because I don't know how it's going to do on YouTube. When this went out and it did really well, it was my favourite project. The one I'm working on now is coming out in June, which is a big thing that's going to EMF. It's not my favourite project because I bit off more than I can chew. And the one I haven't started that I think is going to be really good is my favourite project because it's still in my head. I haven't even done any CAD. Oh, a serious robotics. So it's very hard to... Everyone's seen Boston Dynamics videos of dogs dancing and Atlas going around and doing things. Tesla, Disney Imagineering did those little duckling droids. Obviously, there's loads of companies like Unitree, selling a robot dog for $2,700 that's better than the one I built and costs less than the parts value of the one I built. So it's very hard to make a good video, at least that people will watch, that's me in my back bedroom with a 3D printer, because it's so hard to compete with amazing robots everyone's seen with the results I get. Whereas wheels with the bikes on bikes with the wheels on the wrong way round, no one's seen that, so that's the thing. So it's got to be for the clicks, and part of that is delivering on what you've said as well. If this was rubbish, then it wouldn't have done as well. So yeah, it's very difficult to pick a topic that people all think is good when it's something that you've got people with multiple PhDs and millions of dollars funding.
I think we're excited for what's to come. We've got one more question. We've got this guy down here.
How long did your project take?
This one?
Yeah.
So at the time I was doing videos every 2 weeks, still on YouTube. So I didn't do it in one go. So I started printing the little wheels in December. And I did about 2 or 3 a day on one printer while my printers were doing the other projects I was doing every 2 weeks. So it took quite a while. If I just did it all in one go, I think about 4 weeks. So
sounds like no time at all. Sounds like no time at all. Everybody here, give the biggest round of applause to James Bruton.